When you run a forensic PCR and it fails, it's not some random event. It's actually a solvable problem. In this explainer, we're going to break down the whole process of molecular troubleshooting, how to figure out what went wrong, and more importantly, how to fix it.
You know, a failed PCR reaction isn't just bad luck. It's a deterministic outcome. Every single failure, whether it's a total catastrophe or just a partial result, leaves behind a very specific chemical signature. Your job is to read that evidence. So here's the mindset I want you to adopt. I want you to think of yourself as a molecular doctor. That little PCR tube, that's your patient. It's showing symptoms, and you need to run the right tests, look at the results, and then prescribe the correct cure. It's all about a systematic, diagnostic approach.
When you get right down to it, there are really only two things that can go wrong. First, you could have a biological failure. This means the DNA template itself is the problem. Maybe it's missing or it's degraded. And second, you have chemical failure. Here, the DNA is fine, but the reaction has been poisoned by something we call an inhibitor. The PCR engine itself is broken.
Okay, so before you even think about looking at the final DNA profile, your very first step is to check the patient's vital signs. These are the hard numbers from your real-time PCR run. This is your diagnostic dashboard, and honestly, it tells you pretty much everything you need to know. First up is the CT value, or cycle threshold. Put simply, this just tells you how much DNA you started with. A low CT value means you had plenty of DNA to work with. A high CT means you were starting with a teeny tiny amount. It's your baseline. It sets your expectations. Next, and listen, this one is absolutely critical, is the IPC, or internal positive control. This is a little piece of synthetic DNA that we add to every single reaction. It's not human, so it won't mess with your profile, but it uses the exact same chemistry. So if the IPC works, you know your PCR engine is running perfectly. If it fails, well, you know you've got a poison, an inhibitor, in the tube. And finally, we have the slope of the amplification curve. This tells you how efficient the reaction was. In a healthy reaction, the DNA should double every single cycle, which gives you an efficiency of close to 100%. If you see a shallow slope, that's a key symptom that the reaction is struggling. All right, now that we know what vital signs to check, we can start to look at some of the common clinical cases. We're going to use our diagnostic dashboard to systematically figure out what's going on with each one. Our first case is the most dramatic one you'll see, the flat line. You run your sample, you look at the results, and you get nothing. Just baseline noise, not a single peak. This is a catastrophic failure, but believe it or not, it's actually one of the easiest to diagnose.
So what do? Step 1, check the IPC, always. If the IPC worked just fine, that tells you the reaction chemistry was perfect. The diagnosis? It's a biological failure. There was just no DNA in your sample to begin with. The cure is to go back to the original evidence and re-extract it. But what if the IPC also failed? That's your smoking gun for a chemical failure. The diagnosis is severe inhibition. The cure, and this sounds weird, is to dilute the sample, maybe 1 to 10, and run it again. This waters down the inhibitor and frees up the PCR engine to do its job.
Okay, case number 2, the whisper. You get a profile, but it's really weak, with all the peaks hovering right around the detection limit. This can happen for a couple of reasons, but usually it's a problem with competition during the electrophoretic injection. That's how we load the DNA onto the instrument. So how do we fix this? It's a 2-step protocol. First, repurify your DNA extract. Something like a silica column works great to get rid of excess salts. Why does that matter? Well, when the DNA is being loaded, tiny little salt ions are way faster than the big DNA molecules, and they just outcompete them. If you get rid of the salt, more DNA can get on board. Second, you can just increase the injection time, which physically pushes more of your sample into the machine for analysis. And now we come to the classic forensic artifact, the ski slope. You'll see this one all the time. The profile has strong peaks for the small DNA fragments, but the signal gets weaker and weaker as the fragments get bigger. Now here's the really critical part. 2 completely different problems can cause this exact same pattern. The first is degradation. That's a physical problem where the DNA strands are literally broken into smaller pieces. The bigger DNA targets are just more likely to have a break in them so they don't amplify. The second cause is inhibition, a chemical block. The longer the DNA target, the more likely the polymerase will run into an inhibitor and just fall off. So how do you tell them apart? The IPC is the key. The IPC is a small synthetic piece of DNA, so it can't be degraded. If the IPC looks normal, your diagnosis is degradation. But if the IPC is delayed or failed, the diagnosis is inhibition. Okay, let's switch gears.
Sometimes the problem isn't a lack of signal, it's the presence of false signals. These artifacts, or ghost peaks, can really contaminate your profile. So here's a quick guide on how to spot them. First up, stutter. This is the most common artifact out there, and it's caused by the polymerase slipping during copying. The test is really simple. First, is the mystery peak one repeat unit smaller than a real allele right next to it? And second, is its height less than about 15% of that main peak? If your answer yes to both, it's stutter. You can just filter it out.
Next, could it be -A? This artifact happens when the polymerase forgets to add the very last A nucleotide. This usually only happens when you have way too much DNA. So the check is the peak exactly one base pair smaller than a real peak? And is that real peak totally saturated, just a massive flat-top signal? If yes to both, it's -A. The fix is to dilute your sample and run it again.
And finally, is it pull-up? Now this isn't a chemical artifact, it's an optical one. When you have a massive peak in one color, let's say blue, the signal can be so bright that it bleeds over and creates a little ghost peak in the green channel. The check is purely visual. Just look at the raw data. Is there a giant peak in another color lined up perfectly with your ghost peak? If so, you've got pull-up.
To pull all of this together, we've made a diagnostic cheat sheet for you. You can think of these as the doctor's standing orders for any time a PCR goes wrong.
This table really just maps out the whole logical process. For each thing you observe, you check the status of the internal positive control, and that becomes your decision point. It lets you differentiate the diagnosis, no DNA, inhibition, or degradation, and then it tells you exactly what to do about it. It's a simple but really powerful workflow. Ultimately, all of this troubleshooting, it all comes down to one core principle in forensic science. Reliability is defined by thresholds. We use things like analytical and stochastic thresholds to make objective, numerical decisions about our data. This whole systematic approach is what allows us to separate a true biological signal from all the random noise and artifacts that pop up at the edges of detection.
And that leaves us with the final question that you have to ask yourself every single time. By following this diagnostic process, by being that molecular doctor, you ensure that your final conclusion isn't just a guess based on a fuzzy picture. It's a robust interpretation rooted in the chemistry of the reaction itself, and it's ready to be defended as scientifically sound.